Hello everyone, I'm Cyril Huang from Microsoft Research. Today I'll present our work, High Performance Role Pattern Recognition Using Joins. This is a joint work with Eric and Swajit from Microsoft Research. Sequence patterns are common in real life. Consider the map in Seattle. The police is interested in identifying a sequence of related crimes of type A followed by a few B and then C. And these related crimes should also satisfy some temporal spatial conditions, like within some Joule bounding box and within some time window. Suppose that we have a database where each row represents a crime record with timestamp, crime type, Joule information. So how should we search such row patterns in databases? Can we use drawing or should we use window functions? It turns out to be not easy, especially because of the subpattern of B plus here, which represent one or a few Bs. Fortunately, in the latest SQL specification of 2016, MetricAnalyze have been introduced to perform exactly this task, row pattern search. Next, I'll illustrate how MetricAnalyze work by expressing this related crime pattern we have described just now. So first, we will order the crime table by timestamp, as visualized in the bottom part. Here each record is mapped to this sorted timeline, along with the crime type information. Then we can define the pattern using regular expression. Here A, B plus C means that we start with A, followed by one or more B, and last C. Where A, B, C each is a pattern variable, which we will define later. So we can define each pattern variable using a set of Boolean conditions. For example, we can define independent condition on crime type, and we can define dependent condition on latitude and longitude bounding box, as well as the window size. Hopefully now you have a basic understanding of MetricAnalyze. It is very useful for row pattern search. Because of this, many systems have provided support for MetricAnalyze, including Chino and Azure Stream Analytics. These systems all use non-deterministic finite automata in their implementation. While NFA works well in streaming, it misses several opportunities in historical setting. First, it assumes a fixed order of execution. Second, it cannot make use of indexes. Third, operator-level parallelism is quite limited in the current MetricAnalyze implementation. So the question we ask in this paper is, can we make MetricAnalyze faster by leveraging existing effort on SQL's other constructs? Those constructs have been well studied and well developed. So in fact, when we look at the query, it looks very familiar, right? So it contains filter conditions and also join conditions between A and C. With these observations, we adopted the pre-filtering strategy and proposed to use SPJ query to perform the pre-filtering, safely pruning out rows with no match. This can be easily implemented as a logical plan rewrite rule and allow us to harness several benefits inherent to executing this SPJ query, including joins flexible order of execution, the utilization of indexes, and parallel execution. So we apply this pre-filtering strategy on different systems and do have observed significant gains. As depicted in this table, we can achieve around 5.4 median speedup on Chino with ORC file format, and around 57 times speedup in SQL Server with row store and 41 times speedup with column store. So this is cool. Now it's time to dive into our major insights. So we will continue using this CRUIMES table and related CRUIMES pattern. Given a table and a query pattern, we will first select a symbol set, say A and C. A symbol set is a subset of all possible pattern variables. How to select the symbol set itself is a challenge, and we will discuss it later. Now let's assume that A and C has been selected, and we can use the conditions on A and C to construct feasible ranges. So the first condition in where clause is implied by the sequential order between A and C, followed by independent condition on CRUIME type and dependent condition on latitude and longitude, and then the window condition. After executing this SQL statement, we can obtain 3 feasible ranges, and we can use these feasible ranges to print out irrelevant records. Here we obtain the filtered rows, and this completes the pre-filter phase. It is desired that the number of filtered rows is much smaller than the number of rows in the original table. At last, we can apply NFA-based MATRACognize in these pre-filtered rows. As you may have already noticed, this pre-filter phase can itself be very expensive, especially because it involves range drawing. And range drawing is in general costly. In our example, it would require clustered index on timestamp, otherwise it will time out. So if we do have a clustered index on timestamp, we can achieve around 57 times median speedup on SQL Server with row store. However, indexes are not always available. So here comes to our second insight, bucketize the filter. We can first bucketize the timeline based on window size, which is 1 hour in our example. Our observation is that a row matching A from bucket I would only need to join with other rows in the current bucket or in its next bucket. This is because of the sequential condition and window condition between A and C. Similarly, a row matching C from bucket I would only need to join with other rows in the same bucket or its previous bucket. In this way, we can convert the range drawing into equality drawing on bucket ID. Let's illustrate by continuing the previous example. First, we assign a bucket ID to each row. Next, we generate the bucket range by performing equal drawing on bucket ID along with all other conditions. Each output row here corresponds to a bucket range with candidate match. Here we get bucket 1 to 2, 2 to 3, and 5 to 5. Then we can flatten the bucket range to obtain distinct bucket IDs and use these bucket IDs to filter the original input rows. So now we complete the pre-filtering phase. So cool. Now the only remaining challenge is this symbol set selection. Unfortunately, there is no one optimal symbol set. We performed an experiment on pattern AZ star BZ star C over 100 random parameters. We tried out all possible symbol sets, record its execution time including both the pre-filter phase and MATRACognize phase, and then count the number of times the symbol set achieves the smallest runtime. As we can see from these two figures, there is no one optimal symbol set, and different symbol sets are preferred for different queries and systems. So how do we do the symbol selection? We rely on our old friend cost model. So the cost model consists of two parts. One is pre-filter part and one is match-recognized part. For the pre-filter cost, we reused cost model for SPJ query, but with our own cardinality estimate for distinct buckets. For match-recognized cost, we propose to use the number of transit calls as the proxy of match-recognized time, and then simulate the number of transit calls in NFA based on data statistics. You can find more details in our paper. Putting all this together, given a pattern ABC, we will first generate all candidate symbol set, and then we will select the symbol set with the smallest cost model, for example AC. At last, we will rewrite using AC while bucketized filter. The high-level intuition is that our prefilter-based rewrite is most useful when there exist selective symbols or combination of selected symbols. Now let's look at some experimental results. We performed our experiments with 6 query patterns and 3 pattern variable definitions. For each one, we generate 100 query instances by varying the parameters. We focus on the crime dataset with 6.5 million records and 22 attributes. Overall, Chino achieves 5.4 times median speedup, and SQL Server with column store achieves the highest median speedup of 57.5. This is mainly because drawing is very performant in SQL Server than in Chino. We also performed regression analysis as shown on the right-hand side. So here, each point corresponds to a regression query, which means our proposed method is slower than the base NFA without pre-filtering. We can see 7 out of 1,800 query instances experienced a regression, and the largest slowdown is 1.3 in SQL Server with row store. In summary, regression is insignificant compared to the massive performance gain we obtained. In conclusion, we propose to use SPJ query as a prefilter for improving match-recognize, which can be easily implemented as a logical rewrite rule. And we developed bucketized filter for speeding up the prefilter step. We also adopt cost model for choosing appropriate symbol set. There are more in our paper, like how to handle general patterns, cardinality estimator for prefilter, cost model for match-recognize, and many more experiments. Thank you.